Welcome friends, we are learning digital instruments and in this sequence today we shall try to learn the basics about digital voltmeter. So the major points we are going to discuss today are the DC voltage measurement, digital word, latch, start bit, floating point information, polarity information, auto ranging, polarity detection, auto zeroing, AC voltage measurement and small signal measurement. So let us start with the DC voltage measurement. So we shall start learning about DC voltage measurement using a block diagram of DC voltmeter. So DC voltage measurement. So let us draw the block diagram for DC voltmeter. So we have the DC signal to be measured, which is passed through an attenuator. So here you are getting the DC voltage. So this is V in and this is the attenuator. This goes to the output of attenuator goes to sample and hold circuit. So sample and hold circuit, sample and hold circuit, and an A to D converter. So from here we will get the output of a counter or register which goes bit by bit to the 7-segment display. So we can draw here the SSD or LCD display. SSD or LCD display. So from here bit by bit it goes. Sometimes it goes one by one as the result comes. Sometimes it goes together. So these are called the serial communication or parallel communication. So the output can also go to the recording device. So here we will have a recording device, So from the display unit like this it goes to the recording device. So we have the recording of the display data. Now from the output of the A to D converter we have a signal which is called the start bit that goes to the display unit. So this is the start bit, and the other signal that goes is the latching signal. So it goes to the latch. So this can be a group of signals. So like this I'm displaying. So you have many parameters over here to be discussed. First of all, the DC voltage input which comes into is attenuated because the input of the sample and hold circuit, it can have an input saturation block or an input saturation level, because of which the DC voltage has to be attenuated. So the scaling will be done according to the input saturation level of the SNH and A to D converter, as well as the ripples are filtered out. So once the attenuated signal enters the sample and hold circuit, so here what happens that the signal is sampled at given instants of time that are periodic, and it can be zero order hold, first order hold, or whatever is the algorithm. You can hold the circuit for the conversion process. So the period for which the conversion takes place, the signal is hold to a given value, otherwise the result of the A to D converter will be disturbed. So once the result is produced, here the result comes. Suppose you have 8-bit register, so your 8-bit will complete the conversion here. So after that a start bit is generated. This start bit will allow the signals to flow and be displayed here at the display unit. Now you have to latch the display, because once the display comes, it should be visible for some time, either for observation by eyes or for storing or for recording purpose. So this signal has to be latched for a period of time until and unless the next result of the A to D converter comes. So you have a data which is either stored in the converter, A to D converter, or it is a result of the counter outputs. So whatever be the data, it should be in the form of a combination of digital bits at the output of the converter, which will be analogous to the voltage input, that is the DC voltage input to the circuit. So this data is stored in the form of a word. So the first topic we are going to discuss under this is the digital word. So we have first the digital word. Digital word. So this is basically the data which is available in the form of storage of a register or the outputs of the counter. So here you have the digital word, and there is significance of different data in the digital word. Second one is the latch. So the purpose of the latch is to hold the data at the display unit for a given period of time. So the purpose of this is to hold the display data for a specific period of time. Now the start bit, which we have already discussed, is that the start bit is basically once the conversion is complete, the display unit needs to display the fresh A to D output. So that is the purpose of the start bit. Then next is the floating point information. What is the floating point? So this is, you can get information in many books or on the net. A lot of information is there, but to consolidate the information and concretize, let us understand it in this way. Suppose you have to store the data or present the data in a register. So I am having a 8-bit register. So here I leave the first bit for polarity. Polarity is the sign of the input signal, positive or negative. Then we have to display the 4 bits of the mantissa. So let me tell you what is abscissa and mantissa. ABC dot ABC. So suppose you have say 5.3. So this is abscissa, and this is mantissa. So this is the portion for mantissa. I have to display it from 0 to 9. So for 0 to 9 I have to display the first bit in the form of 4 digits. So 0 0 0 0, 4 digits, and 9 is 8 plus 1 9, like this. And these 3 bits are for abscissa. So here we have data varying from 0 0 0 to 111. So naturally I can display from 0 to 7. 0 to 7 I can display over here. So suppose I have to display 5.3. Here I have taken 5.3. So here 5 is presented as 101 and 3 is presented as 0 0 0 0 1 1, right? So you got the 5.3 displayed as 0, and this is, for the time being I'm avoiding the polarity sign. Now suppose the next voltage to be recorded is 5.34. Then what you will do? You will say that this is 5, so 101, and this is 0.34. So 0.3 I can display with 0 0 1 1. Then where will go the 4? So for 4 I don't have any provision in this word. In this word I don't have any provision for 4. So that 4 becomes the floating point number. This is the floating point in this application. So because for 4 I don't have any provision, so IEEE has defined a technique for this. If this is 5.35 and above, then you assign the bit to be 0 0 1 1 for 3 plus 1 bit. So it will become 0 1 0 0. So 5.35 can be represented by this, and if it is less than 5.35, then you consider it as 5.3, so it will become 0 0 1 1. So that is how we can go for considering the floating point information, and this consideration is the IEEE standards. So next is this fourth one is the floating point, and next fifth is the polarity information. So for this, what you do actually, as we have discussed in point 4, that we have the register, and here we have the provision for 8 bits. So the 7 bits we can keep for data, and the MSB we can keep for polarity. So here if it is 1, then most of the cases it is negative, and if it is 0, then it is positive. So that is how we can take care of the polarity. So let us go to the next topic, that is the auto ranging of digital voltmeters. How we do it? How do we do the auto ranging for digital voltmeters? So let us go for auto ranging. So next topic of discussion is auto ranging. Auto ranging. What is auto ranging? Let us draw a block diagram. So we need two comparators over here to set the lower and upper limit of the auto ranging circuit. Plus minus here, minus plus. Please be careful about the sign. This is the non-inverting input where we are applying a V in whose range has to be detected, and the inverting input is grounded. Then the non-inverting input of the second op amp is supplied with the fixed voltage, which is basically the upper range of the given range, upper end of the given range. So this inverting input is supplied by the same voltage source, and these two outputs of the op amps are digitally ANDed. This digital ANDing of the outputs are done. Here again you can use op amp for digital ANDing, and here you can use a floating point adjusting device. Floating point adjusting device or circuit, and this will give you the range of 0 to 100 millivolt. So how it comes? The voltage we are providing, suppose I am starting from a voltage, I am starting from -5 and it is up to -5 millivolt to 110 millivolt. This is the input voltage, maybe a sinusoidal signal of this pattern. So here the output of a device is V in, which is coming like this. So now this every instant of the voltage is coming into the inputs of the comparators. So as soon as it is below 0, suppose this voltage is 0, so as soon as this is below 0, the output is output of the first comparator. I say first comparator, this is second comparator. So output of the first comparator is negative because 0 is ground is 0 and -5 millivolt is less than this, so this is negative, so this is 0. I take the positive digital system, the negative voltage as 0 and positive voltage as 1. So once the voltage increases beyond 0 at this point, so what happens? The output becomes 1 because 1, so some voltage greater than 0 will be more than the 0 over here, so this is 1. At this time the input to the second comparator is something above 0 but less than 100 millivolt. So here again the output is 1 because the 100 millivolt is greater than the voltage present here. Maybe you are giving 0 millivolt or you are giving 10 millivolt, so it is 1. After some time, when the voltage reaches 100 millivolt and crosses it, then the second op amp output will be negative because the inverting input voltage is greater than the non-inverting input voltage, so this output becomes 0. So as we know, in ANDing circuits, when both the inputs are high, then it will develop a high output. So this will be displayed in the display unit or go to the next stage for processing. Whenever this output is not 1, the further processing, the data available will be 0. So for this output to be 1, we need the voltage input to be the range of 0 to 100 millivolt. As we have understood that when the first op amp is considered for voltage above 0 volt and second op amp is considered for voltage below 100 millivolt, and the ending circuit will definitely combine both these two inputs to keep the range within 0 to 100 millivolt. So in this way we can say that the different ranges can be produced. Suppose I want to develop a circuit for 100 millivolt to 1 millivolt. So the same way we can draw it. So we have the first op amp, this is plus, this is minus, and for the second op amp it will be minus and plus. So the V in should be here and the inverting input should be grounded for the first op amp, and for the second op amp the inverting input should come from the V in, and the second input should have, non-inverting input should have the higher range of the range selector switch. So here it is 1 volt. So this is your this input is actually your 100 millivolt. So again we can see that this combination will sense for input in the range of 100 millivolt to 1 volt. Here you can see that as soon as the voltage is greater than 100 millivolt, the first op amp will generate a 1 at the output, and as soon as the input to the second op amp is less than 1 volt, the output is generated on 1. So the range will be selected through this selector unit. So that facility we have through the selector switch. Now this will go to the output where the range is 100 millivolt to 1 volt. So in this way we can have different ranges. So this should be the range of 0 to 100 millivolt. Then we can have the range of 100 millivolt digital voltmeter to 1 volt, then 1 volt to 100 volt, and from 100 volt to the 1000 volt, because 1000 volt is the voltage, low level voltage measurement. So we can use the digital voltmeter up to 100 volts. Next comes the situation of polarity detection. So let us see what is polarity detection and how we can do it. Polarity detection. So the information about the polarity detection is, as it is provided with the measurement, the polarity of the measurement. This is given in the A to D converter. So as we had discussed, the dual slope A to D converter, where we had seen that the voltage is applied to the integrator circuit. If you remember, we have the op amp with the integrator circuit. So this voltage across the op amp is given for a fixed period of time. So for a fixed time we are giving different voltages, and then it is discharged freely so that we can add up the counter here. Now from here the counter adds up to a final value. Now if this is the positive input voltage, it will be the first quadrant, and if it is in the negative input voltage, this will happen in the fourth quadrant. So that is how we can obtain the polarity of the devices by using dual slope converter. Next is the auto zeroing. So let us see how we can do auto zeroing. This is simple. Once we have discussed, in fact, if you provide a low impedance grounding path to the capacitor which is already charged, then you can discharge it very fast. So auto zeroing. So here what we do, actually we are discussing about the integrator. So you have the integrating capacitor, the output is produced. After integration, the voltage will be developed on both the plates of the integrator but with opposite polarity. So you have the V in for charging. So here the charging happens in this way, so it becomes positive, this is negative. So this is the selector switch. So once it is charged, you can discharge it through a grounding circuit. So once it is grounded, the positive plate will charge quickly through this ground path. So that is how the auto zeroing circuit works. Next, we study the digital voltmeter for AC voltage measurement. So for digital voltmeter for AC voltage measurement. So here you are getting the AC voltage, but you are using digital voltmeter, so naturally we will be developing something which is the RMS equivalent of the voltmeter. So RMS equivalent of the AC voltage measured. So here we are using a phase compensated attenuator. Let us place the phase compensated attenuator over here. Phase compensated attenuator. Then this AC voltage, I write in bracket AC for clarity, is rectified. We are using a rectifier. So a rectifier with filter. So there are different kinds of rectifiers. We have first full wave rectifier, then bridge rectifier, then bridge rectifier with capacitor filter. So their output generated will depend upon the kind of rectifier circuit you are taking. So in case you are taking the rectifier with filter, means that I am trying to take the bridge rectifier with capacitor filter. In that case, the peak of the input voltage is kept with a mild ripple in the output. So we can use the ripple filter at the output, and the capacitor will produce almost equivalent to the peak voltage of the AC supply input to the circuit. So here, once the output is produced, so this output will go to the SNH circuit, S and sample and hold circuit, and A to D converter. So once it is produced, then you know that how we can produce the display. The display will be there as we learned earlier. This is the same method, and this is the recording. So if it is asked in the exam, so the way it has been discussed in the main figure, you have to discuss and draw the figure as it is for the sake of saving time, I am drawing it in short, but actually it has to be shown the way I have drawn it some time ago, like this. This is how you should draw the complete thing. Only thing is that you have to place a phase compensator attenuator and a rectifier in between, because in case of AC voltage you need a rectifier. So let us go a little ahead and see how the digital voltmeter is used for measuring small fluctuating voltages, because digital voltmeter digital voltmeter for measurement of the voltmeter for measurement of signal. So signal means small fluctuating voltage. So we mentioned about signals in case of electronic equipments. We never say that signal in some AC power system or signal in power distribution system, like that. Signal, whenever we are mentioning signal, it is a small fluctuating voltage. So fluctuating means it is AC in nature, but it is not exactly a single sinusoidal waveform. It can be combination of several sinusoidal signals, which is producing a small fluctuating voltage of maybe of very abrupt nature, like this. It can be like this. So this is a signal. It can be as low as 0 to 1 millivolt. So we are discussing here about measurement of signal of the ranges. Here the range is even smaller than this. So this range will be of 1 nanovolt to 10 nanovolt. So how the circuit should work here? Here we should have the circuit as the signal input is attenuated and converted into a phase form using a phase lock loop as we discussed in the last class. So here nanovolt signal. So then we use a quartz crystal to generate 1 megahertz frequency output, and which is sent to a decoding counter or combination of decoding counters. So here you have decoding counters. So basically this clock output of 1 megahertz clock output goes to decoding counters, whose output is again 1 hertz range, and that will basically compare the frequency output of the phase lock loop, and that will be ended, and whenever both the outputs are 1, the output will be 1, and the counter will count all such outputs, which will basically reflect an equivalent voltage to the nanovolt signal input. So here you have counter again. So again we have the display, and we have the recorder. Recording is done over here. So this is all about the digital voltmeters. We need to refer in most of the cases. In practical situations we encounter such type of digital voltmeters, and In the coming lecture, we will learn more about the application of digital instruments that will include current measurement, resistance measurement, and so on. So this is the textbook by Professor A.K. Sahane. We refer to it, and today's matter was taken from this book. You can refer to the book also for your reference, and notes will follow the lecture. So if you find this lecture useful, you can like the video, and if you have not subscribed the video so far, please subscribe it and set the bell icon for notification of next uploads. So friends, this much is for today, and thank you for your patient listening.